Okay, let's get settled and go ahead and click into the clicker question.
Excuse me, what is the clicker competition? For
the recitations are pitted against each other today.
Okay.
Yeah. Is it still going up?
We're at 210.
Is it moving quickly or not?
I would say
it's slow right now.
Okay. All right, let's just do 10 more seconds. Okay. Good job, everyone. All right, let's look through this a little bit, and you can sort of everyone can help yell out some responses. So this was 2s, and that was the correct answer. Which type of orbital is this? 2p. And if you couldn't read this information here, you should have been able to read the information about the nodes. What equation is that for nodes? Yeah, n minus 1 minus L for what kind of nodes? Radial nodes, right. So if you know what it means if L equals 0 versus L equals 1, and you knew this was L, then you could tell if it was an s orbital or a p orbital, and then whether it was 2 or 3p is from the n. So even if you couldn't read this, if you knew that expression, then you were OK. What kind of orbital was in plot C? This was a 3s, L equals 0. And then this is a what? 3p and L equals 2? Louder. D. Right. So do 3px, 3py, and 3pz have different plots? No, they wouldn't have different plots. Okay. So we'll continue to look at this, and we're going to be starting with the handout from last time. Okay, so this is, again, from Monday, page 6. We're talking about orbital size, and we've already looked at this a little bit today, so we should be able to go through this now in a little bit more detail. You've already thought about it. So here we have the 2s orbital, and we're going to have one node using our equation that you just told me, n minus 1 minus L. And when we go from 2s to 2p, here we have no radial nodes. And we can look at our MP, which is the radius of the maximal probability of finding an electron. And you can note that when you go from the 2s to the 2p, the radius actually decreases. So the most probable radius for 2p is less than that of 2s. Now let's consider the 3, n equals 3. So we have the 3s situation over here. And so L equals 0. We have 2 nodes here. And now if you look at the radius, the axis over here, you'll see that the most probable for 2s is close to 5 AO, where AO is the Bohr radius. And over here, you're talking between 10 and 15. So we see an increase in size going this way. And then when we go from 3s to 3p, so here we have 3 minus 1 minus L, which is 1. So we have one node. Down to 3d, 3 minus 1 minus 2, 0 nodes. And you see that there is a decrease here in the most probable radius. So, okay, interesting. All right, so 3D has the smallest, next 3P, next 3S. So there's two different trends we're seeing. One, as we increase L within the same n number, and one going from a smaller n value of n to a larger value, and then again within the 3, within the n value as we change L. So again, to say the same thing a different way, as n increases from 2 to 3, the radius, most probable radius, or the size increases. So from here to here, we have an increase in size. And I just want to make sure people have time to kind of get all of this down, but it should be good. I have a little picture that just shows they're very different in size. OK, so we'll go back to this again. And then, as I also said, as L increases for a given n, so from L equals 0 to L equals 1 here, then we have a decrease in the size. So you can see the most probable radius moves over. And then here is another within n, and n equals 3. We see, again, this decrease. So those are the two trends that you observe when you look at these radial probability distributions. So for exam 1 next week, you should be able to draw distributions like this. You should be able to tell me how many radial nodes you have for different types of orbitals. And you should know these trends in size. So I think in the exam instructions it says up to a 5 case. You don't have to go on forever to be able to draw them, but you should be able to look at these and tell what kind of orbital it is and where the nodes are, be able to draw where the nodes are, 1 node here, 1, 2, 1 node here. This kind of thing will be on the exam next week. All right. So there's something that's a little counterintuitive when it comes to this size issue, and that has to do with how this correlates to the amount of shielding, and as we see later, to the energy levels. So only electrons in the S state here really have any kind of substantial probability that they'll be close to the nucleus. So we have this little blip over here that is close to the nucleus that are at very small radii, very small values of R. Even though the most probable is out here, if we compare 3s to 3p and look at where the electrons are that are closest to the nucleus, they're quite a bit farther away than in the 3s, or there's more probability that there's going to be some closer here. And then the closest probability over here for these electrons is quite a bit farther away. So we see these circles kind of move out. So even though the overall radius, the sort of size of the whole thing, is decreasing, the probability that there are going to be electrons really close is actually going in the opposite direction. And so what this means is that S electrons are the least shielded because there's higher probability that there'll be some close to the nucleus. There's more penetration close to the nucleus. So S electrons are the least shielded. And we're going to come back to this when we move on to today's handout. This is really important in terms of thinking about the energy levels. And I'm going to have these diagrams on the handout for today, so we'll see them again. All right, so before we move to that handout, we got to finish our quantum numbers and talk about electron spin. So the fourth quantum number describes the spin on the electron. And we already saw the magnetic quantum number m. We saw m sub L. And now we have m sub s. And the s stands for spin. So there's some nomenclature that actually makes sense. So there are two possible spin values for an electron. ms can equal plus a half, spin up, or minus a half, spin down. And here are some little pictures of that. So this ms term, this spin magnetic quantum number, completes the description of the electron, but it's not dependent on the orbital. To describe an orbital completely, you only need 3 quantum numbers, but to describe the electron, you need 4. And that is shown again here on this picture, or on this slide. You need 3 quantum numbers. You need n, l, and m sub l to describe the quantum number, describe the orbital completely. But you need a 4th one, this m sub s, to describe the electron. So if you see wave function n, l, m sub l, you say that's telling me what the orbital is. And if we add the m sub s, then you look at that and say, oh, that's going to tell me all the way to the electron what is going on. So this final quantum number led to what we know as Pauli's exclusion principle, which is that no 2 electrons can have the same 4 quantum numbers. They can't have the same, no 2 electrons can have the same spin, in other words. So if we are drawing a configuration for neon with 10 electrons, we're going to have, with 1 electron being up spin, the next one is going to be down. Because if we had 2 of these both going up, they would have the same 4 quantum numbers. And that's not allowed by Pauli's exclusion principle. So when you have 2 here, 1 spin up, 1 spin down in an orbital, then we say that those electrons are paired. And an important thing that kind of comes out of all of this is that 1 orbital can't hold more than 2 electrons. If it did, there'd be another electron that would have the same 4 quantum numbers. Because you need 3 quantum numbers to describe the electron, or the orbital. We need 3 to describe, say, that it's n equals 1, that it's, and then it's s state. So we need those other ones to describe the orbital, and then the 4th one to describe the spin. So if we add another electron, you'd have 2 that were spin up, say, and that just wouldn't work. So you cannot have more than 2 electrons in the same orbital. And this makes a lot of sense when you think about why you would be putting electrons in orbitals that are higher energy. Why not just keep putting them in the low energy orbital? And it's because you can't do that. You can't put more than 2 electrons in. And so therefore, once you filled a lower energy orbital, you got to move up to the next lowest energy orbital, which we'll also talk about today. All right. So that kind of completes our 1 electron systems. And now we're going to talk about multi-electrons, but we're not going to move far away from the topics that we've discussed. Because with multi-electrons, there are several things that are the same and some things that are different, but a lot of things are the same. So we're going to come back to radial probability distributions and energy levels and things like that. All right, so we'll move on to today's handout. So similarities and differences. Similarities, we have the same shapes of orbitals, whether we're talking about a 1 electron system or more. So again, we're going to have our s orbital. So this is my version of an s orbital that you can hold in your hand, where you have it spherically symmetric, and you have probability out in every direction of r that you might find an electron, except at our radial nodes. And then we have our p orbitals, which can be in 3 different directions, where you have nodal planes. So it doesn't matter what you're talking about, 1 electron system or more, you still are going to have those same shapes of the wave functions. Other similarities, again, include the nodal structure, which I just mentioned, whether S is always going to be spherically symmetrical, P is going to have those nodal planes, the angular nodal planes. So that's the same. Differences, though, have to do with the energy levels. So orbitals in a multi-electron atoms are lower, more negative in energy than their corresponding orbitals in the H atom. So let's take a look at this and think about why this is true. So here we have our friend, the hydrogen atom. It has a small z, z equals 1, doesn't get smaller than that. We have our 1s, then we have our n equals 2. And we talked about the fact that in a one-electron system like hydrogen, these are all degenerate in energy with respect to each other, so they're all equal in energy. And then we have our n equals 3, again, degenerate energy levels, and n equals 4 up here. But when you go to a multi-electron system, the first thing that we'll point out is that the energy level is lower. So we have 1s over here. Now 1s is a more negative, lower number. And we can think about this in multi-electron systems. You have a bigger z. So you have more positive charge, and it's kind of hauling all of those energy levels closer. And so it's a lower energy for all of those. So 1s, again, lower. And we have 2s. Again, that's lower in energy. And now, importantly, 2s and 2p are no longer degenerate with respect to each other in energy. So now the 2p system is higher in energy than the 1s, and so on. So we have 3s down here, and then the 3p's. So compared to hydrogen in a multi-electron atom, n is not the sole determinant of what the energy levels are. Now, instead of just n, we have n and L. So let's review. This is good. This is all getting ready for the test. Some equations that you've seen before. And again, equations will be on the equation sheet. You don't have to memorize them. And the equation sheet for the exam is handed out today, so you can take a look at it and see where things are. If I forgot anything, you can ask me questions, and maybe we'll add some more if I forgot any ones. All right, so for a one-electron system, binding energy equals minus the ionization energy equals minus z squared RH, the Rydberg constant, over n squared. And so for hydrogen, z is 1, but there are other one-electron, at least, ions, and then you have to worry about z. All right, what about a multi-electron system? Looks pretty much the same. But now, instead of just having n, we have n and L, because L matters with a multi-electron system. So the binding energy for the electron is minus the ionization energy. That's always going to be true. The binding energy is always going to be equal to minus the ionization energy, which is equal to minus z. But now we have a different z. We have z effective, which is abbreviated z EFF. So this is the effective charge, not the actual charge. And that's squared. And then we have Rydberg constant and n again. So z effective is not the same as z. And it's not the same as z because of shielding. So we talked about shielding a little bit, and I made this point that you need to think about shielding a little differently. It's not just about the average size of the orbital. It's more about the likelihood, the probability that there are going to be electrons close to the nucleus that will participate in that will be affected by shielding. So let's look at some extreme cases now and think about what's happening in terms of this shielding. So extreme case 1, extreme shielding, maximum shielding. All right, so we have the case, we have the helium nucleus. We've moved far in the periodic table. We've left hydrogen. And so what is the charge going to be on helium nucleus? +2. So now we have this electron 1. We're interested in how much this electron is shielded by electron 2, because we got 2 electrons. Now say electron 2 is close to the nucleus, and it's maximally shielding electron 1 from this positive charge down here. So think about this electron. I like to think about this electron 2 as kind of the Elastigirl of electrons. So Elastigirl electron is shielding everywhere, stretching everywhere around that nucleus, just completely shielding it from electron 1, using the full negative charge to really shield. So in that kind of exaggerated case, the z effective is not 2, it's 1. So this electron basically cancels the whole positive charge of this nucleus, really shields that away. And so this is the effective charge with total shielding, maximal shielding that you can get. So now we can calculate what the binding energy, or if we wanted, what the ionization energy would be for this case, given that particular effective charge. So again, the binding energy of electron 1 is equal to minus its ionization energy equal to minus the Z effective squared RH over N squared. And we can plug in those numbers. Don't forget the minus. We can have Z effective 1 over 1. And we calculate this value, which is, of course, just the Rydberg constant, or minus the Rydberg constant, minus 2.18 times 10 to the minus 18th joules. So this is just like it was a hydrogen atom, a one-electron system. So it had 2 electrons, but one of the electrons shielded so completely, it was like a one-electron system. Again, this is an exaggerated case of total shielding. So now let's go to the other extreme and consider zero shielding, no shielding at all. So here we have the helium nucleus. We have electron 1 is now close, and electron 2 is pretty far away. So again, we're asking how much is this electron 1 going to be shielded by electron 2? And in this extreme scenario, electron 2 is not participating in shielding at all. It's far away. I'm not sure what it's doing. Maybe it lost its supersuit and can't find it. It might be at the dry cleaners. We don't know what's going on. In any case, it is out of the game. It is not involved. It is not shielding at all. So in this extreme case, electron 1 feels that full force of the nucleus. So its effective charge is the full, complete plus 2. So we can plug that in now and calculate what the binding energy is going to be. Again, binding energy for electron 1 equals minus the ionization energy for this electron. Same equation. We put this in. But now the Z effective is 2. And we can calculate that. And now we get a value of minus 8.72 times 10 to the minus 18th joules. And this is actually the same as you would get for the scenario of helium plus, which is a one-electron system. Then in a one-electron system, you can use a formula of just Z, where Z is 2, and get your value. So here are the 2 extreme cases for helium. One, it's like a hydrogen atom one-electron system, and one, it's like helium plus. In one case, it's like it just has 1 electron, and in the other case, you have 0 shielding. So extreme case 1, the Z effective is 1. And we have the binding energy that's very similar to hydrogen. And so this is a total shielding case. It shields so much, it's like a 1-electron case. Extreme case 2, you have the full force. So there's 0 shielding, no shielding at all. And then this is like a helium plus case, where you've actually lost that other electron. It's not shielding. It's not even there. So no shielding. And the reality, in most cases, is that you're in between. And you can determine this experimentally. You can measure ionization energies. So if we measured the ionization energy for helium, we would find that it's 3.94 times 10 to the minus 18th. So it's greater than the 2.18 and less than the 8.72. So it's in between. And that's what you find most of the time. The Z effective is in between 0 shielding and total shielding. So we can calculate what the Z effective is actually in this case if we know the ionization energy. So if you know the ionization energy, you can calculate the Z effective, or if you're given a Z effective, you can calculate what the ionization energy should be for that case. And so I told you that it was measured at 3.94 times 10 to the minus 18th. And so in that case, the Z effective, if you plug the numbers in, would be 1.34. And so this number is, in fact, in between the two cases. With total shielding, you would have a Z effective of 1. And with no shielding, you'd have a Z effective of 2. And so in reality, we're somewhere in between in this case. All right, so thinking about this now, let's try your hand at a clicker question and see if you can tell me which of these is a possible Z effective for an element with a Z equals 3. OK, 10 more seconds. OK. So does someone want to say why the other ones are not correct? Actually, why don't you run up there, and you can give them this pen. American Chemical Society pen. Hand up there.
Who had their hand up?
I think it's on.
So in the case of no shielding, the charge would be 3. And in the case of maximum shielding, there's only 2 electrons in the 1s, so it would be 1. So anything below 1 would be beyond maximum shielding.
Yep.
So it's got to be between 1 and 3.
Yep, that's right. OK. So now we're going to talk more about why shielding is important. And shielding really has to do with this order of orbital energy that we all know and are very fond of. So when I show you this, we want to ask the question, why is 2s lower than 2p, or 3s lower than 3p? So let's take a look at this. And we're going to go back to our radial probability distribution. I told you I wasn't going to leave them for very long, and we're back again. So here, again, if we're considering 2s and 2p, so we'll consider this case here, the maximum probable radius is longer. It's greater for 2s than for 2p. But what we really care about when we're talking about shielding is this part right here. And so there are different ways you can express this. You can say that the electrons in the orbital with lower values of L, like 2s is lower than 2p, those electrons penetrate closer to the nucleus, even though we have this trend where the radius decreases with increasing L. So despite this size difference, when you compare this dotted line with this line here, there's more probability that there are going to be electrons near the nucleus with 2s, and that results in this lower energy. So there's less shielding for the s orbitals than for the p orbitals, and as a result of that, with less shielding, because their probability is that they're closer, that they're bound more tightly, you have this lower energy. So that explains this energy difference. So we can look at this now for the 3 system again, for n equals 3. And here we see that p electrons are also less shielded than the d electrons, despite the fact, if you look, that the most probable radius over here is longer for P than for D. But now if we look near the nucleus at the probability that there are going to be electrons near the nucleus, there's a higher probability that there'll be electrons near the nucleus with P than with D. So these are going to be less shielded and lower in energy. And if I throw S on there, now we see S has the most probability here of being closer than P than D. So for a multi-electron atom, the order of energy, we have S lower than P, P lower than D, D lower than F, due to this shielding. So again, you want to be able to draw some version of these diagrams with appropriate features to explain answers. And this all leads into what we're doing next, which is electron configurations. So we're going to think about how we're going to write the electron configurations, and this indicates how you build up in energy. So electron configurations. So first, we're going to fill our electrons into the energy states that are lowest. Nature doesn't want to do a lot of work, so it's going to put them in the lower states. And again, where those energy levels are depends on, for multi-electron atoms, both N and L. And we're going to put them in one electron at a time, starting with the lowest energy state, and heeding the following rules. So there's some rules in doing this. And most of you probably heard some of these before. And if you haven't, I'm sure you'll like them. I know you heard this because I already just told you about that a few minutes ago. We have Pauli's exclusion principle, which says that you can't have the same 4 quantum numbers. So if you put one electron in, and it's spin up, the next one has to be spin down. And Hund's rule, which is one of my favorite rules, I think, in chemistry. And that is when you're adding electrons to the same state, you're going to put them in singly when there's degenerate energy orbitals before a second one enters the same orbital, and the spins remain parallel as you're adding them across. So let's consider these and put some electrons into these, and we'll do this for oxygen, which is a Z=8 system. So first, I want to put them in the lowest energy state. So that's 1s. So I'll put one electron in there. And then I'm going to put the second electron in there because it's the lowest energy state, so I'm going to fill it up. But I'm going to pay attention to Pauli's exclusion principle and put it in spin down. One electron spin up, one electron spin down. I can't put them both spin up because they would have the same 4 quantum numbers, and that would violate Pauli's exclusion principle. So next I'm going to put electrons in 2s, because that's the next lowest energy state. I'll put one in spin up, and then because of Pauli, I'll put the other one in spin down. Next we come to the 2p system, and I'm going to put the first electron in, but I'm not going to pair the second one. I'm going to put electron in the second orbital, both being spin up. And then I'm going to do that again. And so I like to, most people kind of refer to the Hund's rule as kind of the rule of seating on a bus, where it always seems that one person goes in, and even though there are 2 seats, one person takes it, the next person gets on the bus, doesn't sit next to the person who's already there, they take another empty seat, and so on and so on. And so you fill up the bus with one person per bench before all those seats are taken. The next person comes on, sadly, has to sit with someone else. So if you think about that, that's the Hund's rule. You'll always remember to do that. And once you've put one in each, then the next person on the bus has to sit next to someone, and they're going to do that spin down. Because if it was spin up again, you'd have the same 4 quantum numbers. So these are the rules that you need to know to put these in. And then after you do that, you can write an electron configuration that says what you did. So here, we can write it this way. We'll say we have 1s2. There are 2 electrons in the 1s. 2s2, 2 electrons in 2s. And 2p4, we have 4 electrons in the 2p orbitals. And if for some reason the question asks you to specify m sub L, you can do that too. So then instead of just saying 2p4, then you would say 2px2. So there were 2 electrons in px, and then 2pz1 and 2py1. And if you don't write 1, 1 is implied. So you will see this both ways. You will see the 1 indicated, and then you'll see the orbital just listed with nothing. If you do that, you are implying there's 1 electron in there. If you don't mean to imply there's 1 electron in there, don't write it that way, because that's what is implied if that's the way it is. All right, so now let's do a clicker question. OK, 10 more seconds. I think we can get at least 93% on this one. That's not bad, 90. That was a decent guess. That was a decent guess. OK. So I think the trick here was just counting. So the bottom one that some people liked, there are only 6 electrons, and that has more. OK.
Question?
Yeah.
Are the P M sub L locations always filled in order x, c, y, or infinity x, y, z, or is it 2 ground?
Yeah, yeah, you don't have to worry about that. Yeah, that's kind of arbitrary what you put for that. So it just, if it is indicated, then that's fine. But we didn't give you an option that would be different. Yeah. OK. So now you can imagine that if you're writing these electron configurations and you're asked to write an electron configuration for something way down on the periodic table, you would be writing for a very, very, very long time. So you can use information about core electrons and valence electrons to make your life easier. Now, sometimes you will be asked to write the full electron configuration, and it'll say, don't use kind of the noble gas shorthand. Then that's what you have to do. Very important on the exam, read questions carefully. So let's introduce this concept of core electrons and valence electrons. So if we look at the periodic table, we have our 1s1, 1s2. And then we come down, we have our 2 s's and our 2 p's, and then we have a noble gas, and then we come down and we have our first 3s1. And so if we're talking about sodium, we have core electrons, which are the electrons that make up the noble gas element that's on the row before. And then those are usually not very reactive. They're held pretty tight. And the valence electrons, the electrons that do all the exciting chemistry, you lose and gain valence electrons, they're the fun ones. And so those are going to be beyond that noble gas configuration, those core electrons. And so here sodium has 3s1. So we can also write sodium then as bracket neon, indicating the noble gas before, and then just put the valence electrons, the 3s1. And unless it's clearly specified you are not supposed to do that, this will be acceptable. So we can go on in the row of the periodic table in the 3rd period. And so the next one, we would have 3s2. And then we jump over here to the 3 p's. And so on until we get to our next noble gas. So this is pretty straightforward. There are no exceptions on the 3rd period. But when we get to the 4th period of the periodic table, we start to have a couple of exceptions that you will be responsible for. And so it's looking good up here in the beginning. We have now our noble gas. And then we have our valence electron, 4s1, 4s2. And then we start down in the 3 Ds over here. And when we get halfway through, we have an exception. So you have exceptions halfway through and also when you're almost at the end. So instead of having 4s2, 3d4, it really wants to have 5 electrons. And in this case, instead of 4s2, 3d9, it wants 10. So it likes things being half full or totally full. And so you have these exceptions there. So you don't have a d4 and you don't have a d9. And you're responsible for these two. And then in the period right below, same position, same exception. So you can think about this. I don't know if it's 4 exceptions or really just kind of 2 in 2 places. But these are the exceptions you need to know. So in the 5th, it's the ones right below are the same. You're not going to have a D4 or a D9 here. So you bump one up because it's just happier when it has 5 or 10 electrons in the d orbitals. All right, you're also responsible for knowing the orders. Oh, we have a question way up there. Who wants to run? Get some exercise. I don't always see questions, so yell out my name if I don't see people. I am wearing my glasses. That's good. Yeah?
So what happens when we have an ion, like titanium 2
Good
minus?
question. I'm getting to that.
All right, cool,
Okay,
thanks.
hold on a minute. Yes? We're getting to ions. They're right at the end. Okay, so first let's consider what happens when we're not doing an ion. And there are a couple different ways that we can look at this. This is one way to remember. So you just write out 1s, 2s, 2p, 3s, your 4s, your 5s, your 6s, your 7s, and then draw lines. So you go first, you fill 1s, then 2s, 2p, 3s, 3p, 4s, d, 3d, 4p, 5s, et cetera, et cetera, et cetera. That works. That's one way to do it. It's kind of time consuming. Not sure that's the easiest way. The other way that you can do, this is the periodic table you'll be getting on the exam. And you can just remember what's happening at these different cases. So over here, we're filling up our S's. Over here, we're filling up our P's, except for helium. Over here, we're doing our Ds in the transition metals. Over here, we have F. And then in terms of the period numbers, so we have 1 over here. So we do 1s2, 2s2, or 1s1, 1s2, 2s. Then we come over here. We have the 2 Ps, 3 S's, 3 Ps, 4 S's. Then we have 4 Ds and go to 4 Ps, 5 S's, 4 Ds, 5 Ps. And then we can't forget when we get down here that we have F. What number goes here? 4, right. So when you get to principal quantum number 4 is when you start having F orbitals. So if you just remember this, it's going to help you think about what the energy levels, how you're going to write those configurations. All right, so maybe I'll leave this up and we'll do a clicker question now on this. And you have your periodic table available to look at. And then we'll get to ions. This should be 93%, yeah. OK, 10 seconds. Well, 85, that's still pretty good. Okay, so this one was one of our exceptions over here, and we wanted to have no D9, so it just is happier as D10 system. So that's our exception. One of the 4 that you need to know for this. Okay, so now we have our kind of 2 methods of remembering this, and we did the clicker question, and so I'm going to jump to ions. There's one question on this on problem set, so people have been asking about ions. All right, so when we're just here filling up our 4s ones, 4s we're putting in first, and then we're going to our 3d, which is what we just learned about. But what actually happens when you start putting electrons in your d orbitals is that the orbital energy of the d orbitals drops below the 4s. So once they start becoming filled, you have this change that happens. And this is really only important when you're talking about ions. So if we were asking here about this one, so we would normally say, OK, we put our 2 4s in, and then we have 2 3d electrons. But now, because we've started to fill the 3d, if we're going to really do this in terms of energy level, we could reverse the order. And we would accept both of these for the neutral ion. You could do either here. But importantly, if you start ionizing it and losing electrons, you need to think, where are those electrons coming from? Which are the electrons that are easiest to remove? And what happens is that you end up losing the 4s2 electrons. And so the configuration then for titanium plus 2 is just 3d2. And so this is different. Ions behave differently.